West Virginia. Oh well. Let's get joke of the day, because you know you can count on joke of the day. So did you hear about the guy who drank 8 Cokes? Well, he burped 7 Up. I love joke of the day. It's awesome, isn't it? Okay. The other awesome thing is being able to deal with the distance formula. Now what I'm going to do first is I'm going to show you where the distance formula comes from so that you can memorize it a little bit better and you can understand it a little bit better. Because the distance formula, if I just threw it at you, it would look very complicated and very difficult. But when I show you where it comes from, you're going to find out that it's not near as difficult as it seems. So our distance formula is going to give us the distance between 2 points on the 2D coordinate plane. Now we'll have one point that we'll call P sub 1. The subscript is not an exponent, it simply indicates this is the first point. So I've got my first point in the 2D coordinate plane here, and we've got a second point, P sub 2. Again, that's not P squared, it simply means the second point. It's going to sit elsewhere in the 2D coordinate plane. Now, P1 does not have to sit in the first quadrant, P2 does not have to sit in the third quadrant. I just put them in those quadrants so that we can kind of see them spread out pretty good and we can understand what's happening. Now, the coordinates for P1 are going to be x sub 1, y sub 1. Again, those are not exponents. It just indicates this is the x coordinate that goes with the first point. This is the y coordinate that goes with the first point. And then my P sub 2 are going to have coordinates of x sub 2, y sub 2. Again, just indicating this is the x coordinate for the second point. This is the y coordinate for the second point. So I've got those 2 points in my 2D coordinate plane, and I want to get the distance between the two. That distance would be right through here. So what I'm looking for is this distance right here, which I'm calling D. Now, let's think about what's happening here. If I was to take this point right here, and I was to drop a perfectly vertical line right down like this, and then I was from this point to create a perfectly horizontal line like this, notice what I've created. And what exactly is that? Yes, it's a triangle, but it's a special type of triangle. What kind of triangle is it? Yes, it is a right triangle. How do I know that this is a right angle down here? Well, let's think about this. If this is perfectly vertical and this is perfectly horizontal, perfectly vertical, perfectly horizontal is going to make a right angle right here. They're going to intersect at 90 degrees. So I do have a right triangle right here. Now, when you think right triangle, what do you think of? Yeah, Pythagorean Theorem. Right triangle indicates Pythagorean Theorem. So now let's take a look at this idea of the Pythagorean Theorem. Let me slide it down here, give myself a little bit more room. Let's take a look at this Pythagorean Theorem. And when you think Pythagorean Theorem, most people think a squared plus b squared equals c squared. I prefer to think of the Pythagorean Theorem as leg squared plus leg squared equals hypotenuse squared. Simply because a lot of people don't quite know where the a, the b, and the c come from. This is pretty much what it is. Not pretty much what it is, this is exactly what it is. Leg squared plus leg squared equals hypotenuse squared. Now, one of the legs is right here. The legs always branch off at the right angle. Yeah, check that out. Pretty good. I've been exercising lately. Anyways, legs always branch off of that right angle. The hypotenuse comes opposite of the right angle. So I've got a leg right through here. I need to get the distance on that leg. I need to get the length of that leg. Now let's think about how we would get the length of the leg. Well, notice being that this is vertical, what I would do is I would take this y coordinate right here, and I would take this y coordinate right here, and I would subtract the two. Let's think about it. If this y coordinate up here was a 5, and let's say this y coordinate down here, now granted it's in the negatives, well let's go with that. Let's say that it's like a negative 2. What I would do to get that distance is I would say come up 2 and then another 5 giving me a distance of 7. Well, in order to do that, that would be a 5 minus the negative 2. Subtracting a negative is really adding a positive, and that would give me that distance of 7. So the idea is, in order to get that distance, I have to subtract the y coordinates. the y coordinates because this is a vertical distance. So what I'm going to do then is I'm going to subtract those y coordinates, y1 minus y2, but what if I did y2 minus y1? Well, if I flipped it around and did a negative 2 minus 5, I would get a negative 7. But remember, distance is neither negative nor positive, so how would I guarantee that this is neither negative nor positive? Yes, that goes back to absolute value that we've talked about before. So if I do absolute value on this, then I will get just a basic distance of 7. So what needs to happen then is, in order to get this distance, this vertical distance, I need to subtract those y coordinates, but I need to do the absolute value of that. That will give me one of these legs its distance. So I'll say, let's subtract those y's, and remember, technically, it doesn't matter the order in which we subtract them, because we're doing absolute value. So we could do y1 minus y2, we could do y2 minus y1. It makes no difference at all because we are doing absolute value of that. But notice within this Pythagorean theorem, we're going to take that distance and we're going to square it. So I'm going to take this absolute value and I'm going to square it. Now, let's talk about this distance on this leg right here. Now, if to get this distance on the vertical, we would subtract the y coordinates, then what's it going to take to get this distance on the horizontal? Yes, let's subtract the x coordinates. So we would do x2 minus x1, but here again, we need that absolute value because if we do x2 minus 1 or we do x1 minus x2, we're going to get the same number but opposite signs. And since we're talking distance and we're not concerned about negative or positive because distance is neither negative nor positive, then I'm going to do absolute value yet again. So what I need to do then is I need to say, okay, on this second leg, once again, I'm going to do an x1 minus x2 absolute value or x2 minus x1. Doesn't matter because I've got absolute value. But remember, I'm going to take that distance, I'm going to square it. So here again, I'm going to square this. Now, that will give me my hypotenuse squared. Notice the hypotenuse right here was the d that we were looking for. So that's going to give me my d squared, which actually I'm going to go ahead and put it over here. Because whether it's over here or over here, it's all the idea of the equal sign. And so my distance is on the other side. But remember, within Pythagorean theorem, it's distance squared, so I need to take this d right here and I need to square it. Now let me step back for a minute. Two things I want to point out. One is that remember I'm taking this absolute value and I'm squaring it, and remember the point of the absolute value was to ensure that this distance is neither positive nor negative, and I come up with, for instance, a 7. It doesn't have to be 7, but for instance, a 7. Well, if I don't have absolute value on there at all, but instead I square this, then a negative 7 squared would be a 49, but as well a 7 squared is going to be a 49. So my point is simply this: I don't really need this absolute value in here because I'm squaring it. The squaring takes care of this need for a positive or basically a non-negative number. So I'm going to take the absolute value off in both of these cases. So here is my leg squared. My other leg squared is going to equal x1 minus x2. But it doesn't matter the order that I subtract. Just simply subtract the x's and square it. Subtract the y's. Again, it doesn't matter the order because I'm going to square it. I did write down y1 minus y2, but it does not matter the order in which I subtract those y's because I'm going to square it. And in between these two, I'm going to add. And that, again, is my distance formula. Not near as scary after you hear it that way. Subtract the x's, square it. Subtract the y's, square it. Add the two up in the middle and take the square root of the whole thing, and that is your distance formula. Now you may be thinking, now hold on a second, you did subtract the y's first, here you did subtract the x's first. But remember, addition is commutative. So once and remember, my order of operations says, let's do inside the parentheses here and here first. Then let's do our exponents and square it, then let's add. So basically, I'm going to get a number here and a number here, and I'm going to add those two numbers together. Now remember, addition is commutative. So it does not matter the order in which you add. A 2 plus a 3 is the same thing as a 3 plus a 2. So it doesn't matter if I do the x's first and the y's second, or the y's first and the x second. Again, part of the beauty of the distance formula is, listen carefully. Subtract your x's and square it. Subtract your y's and square it. Doesn't matter the order you subtract the x's. Doesn't matter the order that you subtract the y's, because you're going to square it. And you could do your x's first, y's second, or y's first, x's second. The bottom line is, subtract x's, subtract y's, square each one of them. Add it up in the middle, take the square root of the whole thing. So let's take this distance formula, and let me step back a second before I do some examples. If you don't understand this, where it came from, that's okay. It is important that you know this distance formula, that you know how to use it. I just like to show where it comes from so that it makes it easier to memorize, because you're going to have your distance formula memorized. But one of the best ways to memorize it is just simply to write it down every single time that you use it. I've said many times, and let me say it again, I never had to make flashcards. I never had to stare at a paper. I just wrote my formula down every single time I used it, and then I plugged my numbers in, because if you write your formula down that many times, you're going to memorize it without even trying. So in each of these two examples, I'm going to find the distance between the given points. I know I need to use that distance formula, so I'm going to write my distance formula down first and then plug my numbers in. So I've got a big old square root. I'm going to subtract my x's, square it. Subtract my y's, square it. Add them up and take the square root of the whole thing. And remember, it doesn't matter the order you subtract the x's or the y's. So now I'm going to plug my numbers in. Notice this says I want the distance between a 4, 4 and a -6, -2. So I'm going to subtract my x's, and remember, it does not matter the order in which I subtract those x's. Here's x1, here's x2, and then I'm going to subtract my y's. Now remember, with slope formula, we said once we designated the order on the y's, we had to go in the same order on the x's. That doesn't apply here, because I'm squaring each one of these, so it sincerely doesn't matter. Now, as a habit, I do go ahead and tend to go in the same order, but I really don't have to, because I'm squaring each one of those. That takes care of it in the end. Now, according to order of operations, I need to do what's on the inside first, inside the parentheses, and we know that subtracting a negative is really adding a positive in each one of these cases. Inside that parentheses, because of PEMDAS, 4 plus 6 is going to give me a 10, so I have a 10 squared. And here, 4 plus 2 will give me a 6, and I have a 6 squared. Now from there, I know the order of operations says do the exponents next. 10 squared, 10 times 10 is 100. 6 squared, 6 times 6 is 36, and I have 100 plus 36. Now we know that this does not mean take the square root of 100, take the square root of 36, and add the result together. We know that that only applies for products and for quotients, for multiplication and division. Here I have to do exactly what I see in the order that I see it. So I need to add those two up first and then take the square root. Now remember, the square root of 136 means I'm looking for a number that I can multiply by itself to create a 136. There is no number that I can multiply by itself to create a 136. So I need to simplify that radical. So what I'm going to do is I'm going to break down, break down, break down. Like in the 80s, we were breakdancing. So I'm going to break up that 136. Now if you can't think of bigger numbers that you can multiply by themselves to create a 136, at the very least, it's even. If it's even, you know it's divisible by 2. So I'm going to say that this is 2 times 68. And now I'm going to break up that 68. Remember, I'm looking for perfect squares or pairs. When I see a pair, I can take one out and I can dissolve the other one. Now my 68 is going to be 2 times 34. And I do see a pair, but I'm going to keep on breaking this up as much as possible. That 34, now here's the 2's, 34 is 2 times 17. Now, I cannot break up that 17, so I'm stuck here. But notice that I do see a pair of 2's, and when I see a pair, I take one out, and it dissolves the other one. So now then, that means a 2 is coming out, and underneath I have that 2 times 17. Since there's nothing that I can do with the 2 times 17, then I know that that's going to be a square root of 34. There it is. That's the distance between these 2 points on the number line. Now, in the real world, we do not take a tape measure and measure out 2 times the square root of 34 units. That doesn't happen in the real world. In the real world, we would take a calculator and we would calculate square root of 136, or we would calculate the square root of 34. Once we get that decimal value, we would multiply it by 2. In either case, we're going to get about an 11.66, but in my classroom, we don't live in the real world. In my classroom, we live in the microcosm community of that algebra class. So therefore, we're going to leave our answers exact in my classroom. But if needed be, if we needed a decimal approximation, now this is going to be an irrational number, so it's going to go on forever and ever and ever. It's never going to repeat. It's never going to end. So therefore, this is an approximation. I will not use the exact equal sign. I will use my approximately equal sign. But that is how we get the distance between those 2 points. Now, let's take a look at this example. Notice that in this one, we've got a little bit more of complication happening because we've got these square root values in these x's. But we've got this. So we know that our distance formula, because this is what we're doing, is finding the distance, and I'm going to write it down every single time that I use it so that I memorize it without trying. So here is my distance formula, and now I'm going to plug those numbers in. Once again, does not matter the order in which I subtract these x's, makes no difference at all. So I'm just going to go square root of 50 minus the square root of 2. But remember, I'm going to square that. It does not matter the order in which you do these y values, but I'm just going to go ahead and go a negative 6 minus a 6, remembering that I'm going to square it. Now, back here, this is the easy part, because a negative 6 minus a negative 6 is going to be a negative 12, and I'm going to square that. Here's my problem area. Because can I take a square root of 50 and subtract a square root of 2? No, I cannot. They are not like radicals. I can only subtract like radicals. So I need to make some adjustments to turn them into like radicals. Well, that square root of 50, can I make an adjustment out of it? Yes, I certainly can. Because we know that the square root of 50 is really the same thing as a square root of 25 times 2. And we know that whenever we see a perfect square or a pair, we can take, if it's a pair like we saw right here, we're going to take one out that dissolves the other one. Or if you see a perfect square like we see right here, you can take the square root of that out. So when I take the square root of 25 out, the square root of 25 is just a 5, and I'm left with the 2 underneath the radical. So therefore, this square root of 50 is really a 5 square root of 2. So I'm going to change this up to be a 5 square root of 2 minus the square root of 2, and then I'm going to square that. Now remember that negative 6 minus 6 is a negative 12 squared, and so now I can actually take these two numbers and I can actually subtract them. Because this is a 5 square root of 2 minus the square root of 2, and remember 5 of these minus 1 of these leaves me with 4 of them. So I have 4 square roots of 2. Remember, the radicals is what's making them alike, so I'm going to keep the radical and I'm going to work the coefficients. 5 minus 1 will give me a 4. It's a 4 square root of 2, but I'm going to square that. So now what I'm going to do is I'm going to say, okay, it's time to square everything. Squaring the negative 12 is pretty easy because that means negative 12 times negative 12, which is a 144. But squaring this 4 square root of 2 is a little bit more difficult because I need to recognize that when I do 4 square root of 2 squared, what that indicates is a 4 square root of 2 times another 4 square root of 2. That's where people mess up. Oftentimes people will take that square and they'll distribute the power. And so they'll say 4 squared and get a 16, and they'll call it a 16 square root of 2. Or what they the other typical mistake that they make is they'll square the square root of 2 and they'll get a 2, but they'll forget to square the 4. So they'll call it a 4 times a 2 and get an 8. But remember, it actually means 4 square root of 2 times another 4 square root of 2. So 4 times 4 will be 16. And then square root of 2 times square root of 2. Remember, when you take a radical times itself, square root of 2 times square root of 2 is going to be the number underneath the radical without the radical sign. So it's a 16 times 2, and 16 times 2 is going to be a 32. So when I take a 4 square root of 2, I don't get an 8, I don't get a 16 square root of 2, I actually get a 32. Because I need to square the 4, as well I need to square the square root of 2. So I'm going to get a 32 out of this. And then just like we saw over here, once we get to this point, we're going to add the two numbers together. So a 32 plus a 144 is going to be a 176. And just like we saw over here, what that means is, now I'm going to try to find a number that I can multiply by itself to create a 176. I cannot think of a number I can multiply by itself to create a 176. So what I'm going to do is I'm going to break it down, break it down, break it down. I cannot break dance. It's okay. Now remember that 176, it's even, so I can definitely divide it by 2. And 2 times an 88 will give me a 176. Now I can break up the 88. 88 is going to be 8 times 11. And I can break up the 8. 8 is going to be a 2 times 4. And so at this point, notice that I have a pair right here. And when I've got that pair, I can take one out and dissolve the other one. As well, notice that I know that I have this 4, and I know the square root of 4 is 2. So what I'm going to do now, let me step up this way. What I'm going to do now is I'm going to take the 2 out of here and let it sit out front. I'm going to take the 2 out of here and let it sit out front as well. The 11 is the only thing that stays underneath. Now remember, when I pull them out, how do I combine them out there? I multiply them, because this is one great big huge multiplication problem. So 2 times 2 will give me a 4, and so my answer is 4 square root of 11. And that's going to be the distance between those 2 points on the number, or not on the number line, but on the 2D coordinate plane. And once again, if we want to get the decimal approximation, now in my classroom, we don't live in the real world. We're going to leave it exact as 4 squared 11. But if we want to get the decimal approximation out there in the real world, we would punch in that calculator square root of 176, or we would punch in the calculator square root of 11 times 4. Either way, you're going to get approximately a 12.27. And that, again, like I said, no, not a 12, a 13, I'm sorry, 13.27. And that, again, is an approximation because the square root of 176 is an irrational number. As well, square root of 11 is an irrational number. So when you take your square root of 11 and multiply it by 4, you'll get another irrational number. And so that is a decimal that goes on forever and ever and ever. It never repeats and it never ends. So therefore, this is an approximation and not an exact. So hopefully this helps you with the idea of being able to find the distance between 2 points on the number line, not the number line, I'm sorry, on the 2D coordinate plane. And remember, your distance formula simply says, subtract your x's, square it. Subtract your y's, square it. Add the 2 up and take the square root of the whole thing. And remember, it doesn't matter the order in which you subtract the x's, nor does it matter the order in which you subtract the y's, because you're squaring each one of them. As well, it doesn't matter if you subtract your x's first and your y's second, or vice versa, y's first and x's second, because addition is commutative and it doesn't matter the order in which you add. So I hope that helps. Have a great day.